Okay. You want me? I can just make up something.
I mean, like, I think I know what they were. I think it was 900 feet per second, 45-degree angle, and then the 3-foot initial height.
Okay, let's do it. Let's do it. Now, I'm going to need someone with a calculator. I need a calculator person on this one.
I got it. Oh.
Okay. On your test, the numbers are going to come out such that you won't even need the calculator, okay?
They won't look like this, right?
It'll look similar to this, but the big difference is that initial height of 3, if you make the initial height 0, things work out much better. Because in that quadratic, you don't get that constant term. You can take out a t, and you get t equals 0, and then the other one is easy to solve. You don't have to use a calculator. Liam?
I'm going to ask you to tell me on the test, but we're going to use the quadratic equation because this one you had to.
This one we have to. The one on the test you won't have to.
Okay.
I'll tell you that right now.
So in the test, we'll be given the same initial information.
You'll be given this initial information, but I'll tell you, h will be 0 instead of 3, and that changes things and makes things much easier. Yeah. Yeah. All right, so let's do this. The things we want to do are typical of projectile motion. Given these initial conditions, we want to find time in flight, we want to find the range, we want to find the time at which max height occurs, and we want to find what the max height is. Those are the things I ask you about. So let's do it. First thing to do is realize that the position is given by v sub naught cosine theta t, x component, the y component, negative 1/2 gt squared, plus v sub naught sine theta t plus h. Okay. Now, the initial conditions are such that v sub naught is 900. The cosine of 45 is 1 over the square root of 2, or square root of 2 over 2. We're going to use feet per second, so the g would be 32. V sub naught is 900, like we said. The sine is square root of 2 over 2. And h is 3. The h is 3 is what makes this a pain in the neck. Okay. So you end up with 450 square roots of 2t. That's the x component of your position at any time t. You get negative 16t squared plus 450 square roots of 2t plus 3. That's your position at any time t. First thing, let's do time in flight. This is certainly something you'll be asked. You find the time in flight by doing what? How do you find the time in flight?
Set the y component equal to 0.
Yes, exactly right, David. And away. You set the y component equal to 0.
Why is it negative 16t squared?
G is 32 feet per second when we're dealing with feet per second. Okay. All right, so this is the quadratic equation. This is where you need the quadratic formula, okay, to do it. This is why if h is equal to 0, if this is equal to 0 instead, you simply factor out a t. One value of t is 0, and the other you can find by solving a linear equation, and it's much simpler. So here's what I need someone to do. I need someone to do this quadratic equation and give me a decimal, because that's what you're going to get, some decimal here. You're going to get two answers. One answer will be some negative number very close to 0, and the other one will be the one we're looking for. Because what you're doing here is doing this. You got initial height of 3. This is your projectile motion. But if you extend this, this gives you one value of t. It gives you that negative number that's very close to 0. We don't care about that. It's the other value of t that we care about that will give us the time in flight. So if you set this equal to 0 and solve it, you're going to get two values, but it's only the positive one that we care about. And we'll just round it to nearest tenth or something.
39.8.
Okay, thank you. 39.8 seconds is the time in flight. That's a long time. Well, that's initial
Right.
velocity is very significant here. This is like a rifle or something, right?
Yeah.
Michael Jordan dunking.
Yeah, there you go. Yeah, that's
Maybe
cool.
I just didn't hit enter with like my hand tied behind my back and my eyes were open, so Lexon got mad.
I don't know. Could be. 39.8 seconds in flight. We want to find the range. Now, how would you find the range?
Plug that time into the X.
You bet you would. Exactly right. Take this into the X, so the range is going to be approximately 450 square roots of 2 times the 39.8, and that is going to be a hefty number. I don't know what it is, but it's a big number. Somebody have that?
25,328.6.
Sounds good to me. 25,000, what was it again, Liam?
328.6.
Fine. That's the range. That would be the x-coordinate of this point right here. The other thing it would be to find the time at max height. There are a few ways of doing this. One way that works with this is to take the two time values that you had, the 39.8 and that other one that you had, that negative number one, add them up and divide by 2. That works because the time at max height is midway between the two zeros here. Another way that works, how do you maximize a value? How do you maximize this y coordinate? You take the y and you set its derivative equal to 0. So that will give you the time as well. So both ways work. Since I don't have that other number back here, I'm going to do this. I'm going to take my y component, take its derivative, and set it equal to 0. So the time at max height would be a negative 32t plus 450 square root of 2, and set it equal to 0. This t will give me the time at max height. So it would be, t would be approximately 450 square roots of 2 over 32. Whatever it is. It would be really close to 20 because it's really close to half this, although it's a little bit off.
19.8.
19.8 sounds good. Thank you. That's the time at max, where the max height occurs. What is the max height? How do you find the max height? You bet. Exactly right. So the max height occurs by taking this time and substituting it into our y component. So it would be a negative 16, 19.8 squared, plus 450 square roots of 2 times 19.8 plus 3. Holy mackerel. The max height would be, I don't know what it is.
6,331.1.
Sounds good to me.
So you plugged the 19.8 into the original,
Yes, into the original for t.
just the y component?
Just the y component. That's what this will give you. That's everything you're going to need to know.
It wanted 3 decimal places, so I'm wondering if that must have been like what I messed up.
Could be.
I
I don't know.
why you need 3 decimal places on a number.
I have no idea.
If you do it on a calculator, copy and paste your answer to another line because it sometimes rounds it.
Yeah,
It doesn't like
that's
the way-
probably my problem.
Yeah, it could be. I don't know why. I have no good reason why it's 3 decimal places. I don't know. All right, what else you want to do?
Or could you do a normal?
A normal and unit tangent and principal unit normal, or normal and tangential components of acceleration, or both?
The first one.
Okay.
You need the first one to calculate the second.
All right. Is everybody else set on this? Yes, you do need the first to calculate.
The tangent is just the derivative of the R equation over its magnitude.
Yeah, that is correct.
And then the normal is the derivative of the tangent over the derivative over the magnitude derivative.
Yes, but you're not going to use that. What you're going to do, at least in two spaces, you're going to swap them and take the opposite of one of them.
Could you go over that process?
Yeah, let's do one of those.
Yeah, WebAssign wanted us to find the normal, and I wasn't about to do that.
Well, in three space or in two space? If it's in two space,
But there was one where if you used our trick, it's undefined because you get 0.
oh, it could be.
So if you didn't know the proof, you wouldn't know that.
Oh, yeah, they throw one of those at you.
'Cause it
I'm
was,
not going to do that.
It was 6 over x
Is that right?
for the y coordinate. So if you flipped it around and did the negative, it ended up being that over 0 on the bottom. It's undefined.
Oh, man, that's a bummer. So you had to do the whole thing out?
You didn't have to do the whole thing out, but you had to know how it's done and know if there'd be a 0 on the
You,
bottom. I
you
didn't
had
remember
to
exactly, but I
hit
remember it was
practice
1 over x.
another, and then like enter in a fake answer and get
Oh,
the,
jeez.
and then plug that in.
All right, let's do. Let's do something here. Let's do. I don't know. You have one in mind, David, or what? Or we could make one up.
We'll just make one up.
Yeah, let's
Go
make
with
it up.
like T.
T 1
to
over
the-
t.
Do something t squared. In it.
It's his question. Go ahead. T squared.
Like 3t squared.
To battle.
There we go. T 3t squared. Now, what you should do
This is like kind
is plot this. You should graph this to see what's going on. I think it's extremely helpful to do that plot. T, 3t squared. What you're plotting here is y equals 3x squared. Okay? Okay, that y is 3x squared. So it's a parabola moving up this way like this. Okay? On the other side, but we won't need the other side. All right, here's what we're going to do. We're going to find velocity, acceleration, unit tangent, principal unit normal, tangential and normal components of acceleration.
When you did that
Yeah,
graph,
that's exactly what
you
I
just
tried.
graphed the 3t squared
3x squared.
or 3x. What about the key?
This here, in a vector valued function, is the same as this parametrically defined function, which is the same as, more or less the same as, y equals, now t is x, 3x squared.
So if the 3t squared were in the x or the I unit vector place, it would be.
The other way around, yes, it would be. It would be that. Exactly right. All right, you ready? Let's do velocity. Derivative of position. 1, 6t. Acceleration. The derivative, second derivative of position, the derivative of velocity, 0, 6. Okay. Speed, that's another thing. Magnitude of velocity. Okay. Square root of 1 plus 36 t squared. Okay. Let's pause a minute here. Let's do this at t equals 1. At t equals 1, this point right here would be 1, 3. That would be the point. The velocity vector is 1, 6. Okay. Okay, that's a velocity vector. The acceleration is 0, 6. Something like. Okay. The speed is square root of 1 plus 36 t squared. At t equals 1, it's a speed of square root of 37. But the speed is changing all the time here, okay? As the t increases, the speed is increasing. This is increasing in its velocity. Okay, that's what we have so far. Let's do the unit tangent. Unit tangent vector is equal to r prime over the magnitude of r prime. It's equal to velocity over speed, okay? it's equal to 1/6t, the velocity, over the speed, square root of 1 plus 36t squared. Now at t equals 1, that unit tangent is going to be 1/6 divided by the square root of 37. So what it would be is a vector along the velocity vector, as a part of the velocity vector, okay, made into a unit vector. It's a velocity vector made into a unit vector is what it is. Okay. The tangent, the unit tangent, there's two tangent vectors at this point, one outward and one inward. And we want what's called the principal unit normal vector, and that is the one that's pointing inward.
And that's at a right angle to the velocity vector.
Yes, it is, always. So we want this guy here. And the way to get that principal unit normal vector is to take the unit tangent vector, swap the two x's and y's, and take the opposite of one of them. Okay? Which one? We want the opposite of one of them, the one that gives us this vector. And which one will that be?
That would be the 6.
That would be the 6. That's exactly right. Because the x component goes to the left, the y component, it's perfect.
Is it usually the x component that you switch signs?
For parabolic functions that are opening up, yes. For parabolic functions opening down, it'll be the other way around. But you have to look at the graph. You just have to look at the graph. Those are the tangent, unit tangent, principal unit normals. Okay. We could do the principal unit normal in general, which I didn't do. Let's do that. In general, we'll take the tangent, we'll swap it.
When you say in general, you mean just the symbolic representation of it?
Yeah. Not at that particular point, but at any point. You got to be a little bit careful here, too, because sometimes when a graph changes the direction, like a sine wave or something, inward would be this way, and then when it's over here, inward is the other way. So it changes. And that's probably where you get that point. Right at that point of inflection there is where it's undefined, because it goes from this way to this way, and at that point is where it's undefined.
Negative 6t.
Now, yeah, we got to take the opposite of one of these, and it would be a negative 6t. Okay. Okay, let's find the tangential normal components of acceleration. The tangential component of acceleration, how much of the acceleration is directed along the tangent line? How much of this is directed along the tangent? And that's equal to a dot t. All right. A is equal to something or other here, 0.6 dot t. T at this point is, okay. I'm doing this at that point t equals 1. So when you do the dot product, you get 0, you get 36, you get 36 over the square root of 37. That's the amount of acceleration along the tangent line. How much of the acceleration is along the normal line? That's a dot n. Where n is the negative 6, 1, square root of 37. And that's equal to 6 over the square root of 37. Okay? And what it's saying is that more of the acceleration is directed along the tangent line, 6 times as much of the acceleration along the tangent line as opposed to the normal line. Okay? And in some problems, that would be useful. Liam?
So those are the magnitudes of projections, right?
Yes, they
If
are.
you want to put those into vector notation, you just multiply them through by their corresponding unit vectors, the tangent and normal ones?
Yes.
Okay.
Yeah. Yep, that'd be exactly right. Yep. Anything else? Go ahead.
Question over the sign.
Go ahead.
It gives you the vector function of RT equals 5ti minus 3tj, and it wants you to get the normal.
Okay, you ready?
And I already have the tangent, which is in vector notation 5 negative 3 over root 34.
Whoa. So you have the tangent,
Yeah.
which is what again?
It's 5i minus 3j over root 34.
3, you said?
Yep.
Over square root of 34?
Yeah, and I'm not really sure how I'm like
That's right.
corresponding the normal to it.
Okay, let's do it. All right, let's take a look at this first. Okay. All right, you've got this vector value function, 5t, 3t. What the heck does that look like? You've got x equals 5t, you've got y equals 3t. If you were to solve for t here, you would get x over 5. So y would be equal to, t would be x over 5, 3/5 x. This is going to be a line, 3/5 x. Oh man, I missed it there. Okay. Okay. This is your vector valued function.
How do you go to formulate that y equals thing?
What I did is solve for t,
Oh,
x over 5, and replace the t with x over 5. That's the usual way of solving, of eliminating the parameter. The only exception to that really is when you have those trig functions and you isolate a sine or a cosine and then square both sides, that kind of a thing. So y equals 3/5 x is our, that's the graph, so that's what it looks like. Unit tangent vector, r prime over the magnitude of r prime. R prime is going to be 5, 3. Magnitude of r prime is the square root of 34. Wait, where did this negative 3 come from? Dylan, why do you have a negative 3
I
here?
have no idea.
That should, I don't know. This should be a positive here. This should be a positive.
Well,
I'm going to tell you because it doesn't matter. 5, 3, 5. Yeah, it does matter. It matters. It makes a big difference, actually. All right, it makes a big difference.
you want to see it?
What? It gave you the right answer?
Yeah. I don't know.
It gave you the right answer?
Yeah.
Well, I'm confused.
Me too.
You're telling me.
What happens if you put in 5 with a positive 3? I'd be very curious about
It's
that.
gonna like do anything now. Well, I already have that one right.
Well, now you're going to have it wrong. No, you should have it. It's 5-3.
That was undefined.
Yeah, I'd say that's wrong. I don't know.
Wait, give me the original function. You sure the original function is 5t, 3t? That can't be it. It's got to be 5 negative 3t.
Oh, minus 3t.
Oh! All right, here's minus here. So this is minus. You're right, that's all. That's right. That's all right, not a problem. Negative here, negative here.
Oh, so negative.
Oh, so the line is wrong. Oh, no. Oh, no. No problem, no problem. We got it. All right? So the line is like this. There's a line. That's okay. So, unit tangent is 5. Did they ask for it at a particular point? It's the same everywhere, but so if we do this at 0, 0, say, the unit tangent is 5, negative 3. It's like this. Okay.
Wow, we got it. It's undefined.
Yeah.
Yeah, this is the one I was talking about. It's undefined.
Oh!
So you have to know, like,
Because then if you were to like
They want the normal.
if you
Oh wait, I did. Okay, the tangent. This is the normal. I'm sorry. The tangent is this one. I'm sorry. I did this wrong. It's 5, -3. This is the unit tangent. It's right along the line. I'm sorry. This is the unit tangent. And you're saying the normal is undefined?
That's what it says here.
Either then would work.
Yeah.
Okay, let's do it.
With the derivative definition of it, you would get 0.
Oh, you get 0. Okay, because of this line thing. All right. Okay. Okay. All right. So that's what happens there. Because when you take the derivative of this, you get 0, and the r prime, the magnitude of r prime is 0, and you get 0 over 0, you get undefined. That's what, and that's the answer they want.
Booyah.
Okay, that's it. All right, cool. Any other questions?
that's everything.
Go ahead. That's everything right there. Go ahead. No, it's not everything. Omar has a question. Go ahead.
It's a question about line intersection. It's one of those tutorials, so I can't go to the next part until I complete the first one.
What is it about?
Line intersection.
Line intersection. This is the last chapter.
Is it?
Oh man, Omar, you're back a ways.
Alright.
Oh, you got it? Yeah, I'll do it, but it's just that it's not on this test. It was on last test.
Okay, this one's better for this chapter.
Oh, this one's this chapter? Okay, let me see. So you got it? Go ahead, give it to me.
So find the tangent normal acceleration.
Okay.
So r of t equals t squared of I
T squared, yeah.
plus 2t
2t,
at t is 1.
and t is 1.
Yeah.
Let's do it. Okay? Now, let's set up the graph. Now, we get the t squared in front here, so it's a little bit different. So what do we got? You got x equals t squared. You got y equals 2t. If you solve for t here, you get y over 2. So x is equal to y squared over 4. And what is that? That's a parabola that opens to the right. Okay? It's this. It's not a function. Not that that's necessarily bad, but it's going to look like this. Okay? So, that's what we have. What do we got to do? Velocity and acceleration? At t equals 1?
You just have to find the tangent normals.
All right, well, let's do it. Velocity is going to be 2t, 2. At t equals 1, that's equal to 2, 2. That's the velocity. At t equals 1, you get 1, 2. You get this point here. Okay. At t equals 1, you've got the point 2, 2. You got this as your velocity vector. Acceleration, you've got 2, 0. Doesn't matter where you are, that's always the acceleration. 2, 0. That's your acceleration. This is your velocity. This is acceleration. Okay. You want normal and tangential component? Oh, you want unit tangent, principal unit normal.
Yeah.
Okay. Tangent. R prime over the magnitude of R prime. Okay. R prime is your velocity, 2t2. Magnitude in general is 4t squared plus 4. At t equals 1, we get 2 over the square root of 8, which is 2 square roots of 2. So we end up with 1 over the square root of 2, 1 over the square root of 2. Okay. So that's our tangent here. Our normal, let's swap these guys. And let's take the opposite of one of them. Well, which one? We want the one that's going this way. So which one do we take the opposite of? First component or second?
First.
Second. You want the y's to go downward, and the x's to go positive. So it's the second. At this point, we'll get 2, negative 2 over the square root of a, 2 square root of 2. So we'll get 1 over the square root of 2 and a negative 1 over the square root of 2. Okay, and that'll be this one here.
So could we make a generalization that if you have a vector value function like where you have a quadratic for the first term and a linear for the second term, then you take the opposite of the second component, and vice versa if you have, you know, the linear in the first term and the quadratic in the second term, you can take the opposite of the first component when you take in normal.
My first reaction is no, we can't do that because
it depends on the direction of
yeah, it depends on the. If you had a negative thrown in there, even though the t is squared here, you know what I mean? That would reverse this. If this were y equals or x equals negative, the opposite of y squared over, it'd be going this way.
Wouldn't that make them both negative if it was opening to the left?
If it's open to the left, no. If you have this, that opens to the left.
I mean both of the values of n.
I'm not sure. I'd have to do it out. Your velocity would be going, depends, your velocity could be going this way and this way. It would be both, no, because this one's already negative. Okay, this one's negative on the y's because it's headed downward. So the y's would stay negative. It's the x that would change. I don't want to make a generalization like that. I think you're way better off looking at the graph and coming up with the solution that way. You're much better off that way,
So
David.
this time, why'd you solve for in terms of x?
So I could do the graph. I knew what the graph looked like.
Yeah, it depends on what point you pick too.
Yeah, it does. This point here, as opposed to this point here, that would be different too, because this point gives you this, and here it's the negative part. Okay, when you do this, the x component is positive, the y is negative. When you swap them, you want them both positive. So you're way better off doing the graph, locating the point, and looking at it, rather than try to memorize some generalization. That's my advice. That's my best advice to you.
Oh, I see. You did in terms of x because you have the linear term for y, so you just use that to solve for t.
Yes. All right, how are we doing? You guys all set? See you tomorrow.
Shaking your hand tomorrow.